I'm P. Mabu Hussain, Assistant Professor in EEE Department from Institute of Aeronautical Engineering, Hyderabad. In the previous video, we discussed about the calculation of inductance for a single circuit transmission line. And this video is the continuation to the previous video. And in this video, we are going to calculate the inductance of a double circuit transmission line system. So the formulas we need to remember for calculating the inductance of any transmission line will be given here in the slide. So for a single phase transmission line, the inductance per conductor per meter length will be calculated by using the expression 2 into 10 power minus 7 ln dm by ds. Here dm is the mutual GMD and ds is the self GMD. And for a single phase transmission line, ds value can be calculated using 0.7788 R, and dm here is the mutual GMD, which will be the spacing between the conductors in a single phase transmission line system. So then, if you want to calculate the inductance of a single circuit three phase transmission line, then the inductance per phase per meter length will be equal to 2 into 10 power minus 7 ln dm by ds. And here also the value of ds will be same as for the single phase line, so which is ds is equal to 0.7788 times the r, and r here is the radius of each conductor, and dm here is the d1 d2 d3 whole to the power of 1 by 3, and d1 d2 and d3. So these are the distances between any two conductors in the three phase line. Now here for a double circuit three phase transmission line system, the inductance per phase per meter length will be calculated by using the formula 2 into 10 power minus 7 ln dm by ds. Here the value of ds, which is the self GMD, will be equal to ds1, ds2, ds3. So here ds1 is nothing but self GMD of conductor 1 in section 1, and ds2 is self GMD of conductor 2 in section 2, and ds3 is the self GMD of conductor 3 in section 1 whole to the power of 1 by 3, and dm can be calculated using the expression dab, dbc, dca whole to the power of 1 by 3. Now here the value of dab, dbc and dca, so these are the mutual GMD between the conductors a and b, and mutual GMD between the conductors b and c, and mutual GMD between the conductors c and a, like that, right? So for calculating double circuit transmission line inductance, we are going to use these equations, right? In the previous video, we used these equations for calculating the inductance of a single circuit three phase line. Okay, and this single circuit three phase line may be having three main configurations, right? First, in the first configuration, all the conductors were equally spaced, right? Equally spaced transmission, which is nothing but the line is a symmetrical line. And in the second configuration, the conductors, all the three conductors will not be spaced equally, which means that there will be a asymmetrical spacing between the conductors. On the third case, we place the conductors on a horizontal plane. So then when you place the conductors on a horizontal plane also, the distance between the distances d1 and d2 may be the same, but these not will be equal to d3. So here the conductors when they are placed on a horizontal line also comes under the asymmetrical transmission line. Now we consider all the three cases and we calculated the inductance for all the three cases for a single circuit three phase transmission line. Okay, now here we are going to see the double circuit transmission line calculation of inductance, and we also seen in the last video that if a three phase single circuit transmission line is having two conductors per each phase, then also how you can determine the inductance, that is also discussed in this numerical problem, right? So now come to the numerical problem number 5. Here we are going to find out the inductance of a three phase double circuit transmission line system. Okay, so once read the problem. So find the inductance per phase per kilometer of double circuit three phase line, which is shown in figure here. Okay, the conductors are transposed and are of radius 0.75 centimeter each, and the phase sequence is given as ABC here. Okay. So now in the it is a double circuit 3-phase transmission line system. Why? Because here if you observe the figure, you are having two sets of 3 phases in this system. Right? This is one set of 3 phases and this is another set of 3 phases. So this type of transmission line system is called a double circuit 3-phase transmission line system. Now for this case, we need to calculate the inductance per phase, right? And for 1 kilometer length of the cable, we need to 1 kilometer length of the transmission line, we need to find out the inductance, right? And the radius of each conductor is given here as 0.75 centimeters. Okay. Right. Also, if you see the problem, so the conductors are transposed here. So the conductors are transposed here in the sense at regular intervals, the position of the conductors will be changed throughout the length of the transmission line. So why we use the transposition means when you use the transposition, then you will get the balanced receiving end voltage, so that the efficiency and regulation will be calculated easily. And also if the conductors are transposed, then the inductance in each phase will be the same. If the conductors are not transposed, the inductance in each phase will not be the same, right? So as the conductors are transposed, the inductance for each phase is same. If you calculate for one phase, the remaining phases also will be having the same inductance. Okay, right. Now for calculating the inductance of a double circuit transmission line for one phase and for 1 meter length, so the formula is 2 into 10 power minus 7 ln dm by ds here, and dm is the mutual GMD and ds is the self GMD, and the value of self GMD you can calculate by using the expression cube root of ds1 ds2 ds3 here. So ds1 ds2 ds3 again are the self GMDs of conductor A in section 1 and self GMD of conductor B in section 1, self GMD of conductor C in section 1, right? And dm is the mutual GMD. This will be calculated by using the expression cube root of DAB, DBC and DCA, and DBA is the mutual GMD again between the phases A and B, and DBC is the mutual GMD again between the phases B and C, and DCA is the mutual GMD between the phases C and A. All should be in section 1 only. Right, section 1 here is in the sense as the transmission line is transposed, so it will be having the position of conductors will be changed at regular intervals, generally 1/3 length. Okay, 1/3 length will be considered as a one section. Right, if you take a entire transmission line system, so then in this total length of the transmission line, after 1/3 length, the transmission line conductor's position will be changed. Right, in the first section, the conductor A will be in position 1. Conductor B is in position 2 and conductor C is in position 3, right? So these are the 3 conductors in position, so in section 1, right? Now, after 1/3 distance, now this conductor A will take the second position and conductor B will take the third position and conductor C will take the first position, right? This is called the transposition, right? So then again after 1/3 distance, again the position of the conductors will be changed, right? Here while calculating the ds and dm values, we will consider only the section 1, and for the remaining section also the ds and dm will be the same only. Okay, so we are going to calculate only in one section the value of ds and dm. Okay, now GMR of conductor is nothing but, so this GMR of conductor is the R dash, so this R dash is equal to 0.7788 times the R value. So this R dash is called the geometric mean radius, or simply you can call it as a GMR. Now here R is the radius of each conductor, and the radius of each conductor was given in the problem itself, which is 0.75 centimeters. So if you substitute here, you will get the geometric mean radius as 0.7788 times multiplied by 0.75. So then you will get the value as 0.584 centimeters. Right. So this is the geometric mean radius value, which is R dash. Okay. So then, so to calculate the as a DS, you need to find out the DS1, and you need to find out the DS2, you need to find out the DS3. As well as for calculating DM, you need to calculate the DM, DAB, DBC and DCA. How these will be calculated? So let us see here. Right, before calculating those DS and DM values, you must have all the distances between all the conductors in the given configuration. Right here, if you observe the figure here, so the distance between A and C is given as 4 meters, A and C dash here. Okay, one set of conductors are placed from top to bottom like A, B, C. In another set, in the reverse direction, they will be placed to get the minimum inductance, so that power transfer will be maximum. Right here, the distance is mentioned in the diagram itself. The distance between A and C dash is 4 meters, and between A and B is 3 meters, as well as B and C also 3 meters. And the distance from B to B dash is 5.5 meters, and C to A dash is 4 meters. It was given here in the diagram itself. Right. So now you need to calculate the remaining other distances. Right. So the distance from A to B. Right. So the distance from A to B here is this distance, center to center distance. Always you have to consider. Now what is this distance? So this distance is not given in the problem. So you need to calculate the distance DAB. So how you can calculate DAB? For calculating the distance DAB, you have to make one right angle triangle here. Right. So you draw one line perpendicularly from A up to the line B dash, so that you are getting here a right angle triangle. Okay. So now here, if you see the similar way between C and B dash also, if you draw one perpendicular line from C dash to B dash, here you will get another right angle triangle here. Okay. So now for here, from center to center, this distance is 4 meters. Now here from B to B dash, this is 5.5 meters. Right. Now from 5.5 meters, so if you remove 4 meters, then you will be having 1.5 meters here. Right. So that means from here to here, this distance and this distance. So these two distances value will be equal to 1.5 meters. Right. Now if you divide this, then you will get 0.75 meters for each distance. So this will be the 0.75 meters, and this also will be the 0.75 meters. Okay. See here. So to calculate the AB distance, we draw one perpendicular line to make the right angle triangle, and this distance here is the 0.75, and also here this distance also 0.75. Now here to here, the distance is 4 meters. Now 4 meters plus 0.75 plus 0.75, you will get totally 5.5 meters. Right. So now the value of this is known, which is 3 meters, and the value of this is known, which is 0.75 meter. So then the value of AB, so which is the distance from A to B, so will be equal to under square root 3 square plus 0.75 square you will get according to the Pythagoras theorem. Now if you calculate this value, you will get 3.1 meters. Right. Similarly, you can calculate the distance from A to B dash. So what is the distance from A to B dash? A to B dash here is nothing but from this A to this B, center to center distance. Now here also the distance DAB is not given in the diagram, so you need to calculate from the given values. Here also you have to make one right angle triangle. Now from center of the B, you draw one perpendicular line. Right. Now here from here to here, the value is 0.75 as we discussed previously. Right. So now this distance is 3 meters. Now this total distance will be 4.75 meters. Now according to Pythagoras theorem, this distance you can calculate as under square root 4.75 square plus 3 square. So the distance from A to B dash will be under square root 3 square plus 4.75 whole square. So this value, if you calculate with calculator, you will get 5.62 meters. Right. Similarly, the distance from A to A dash you can calculate using the same procedure here. So now you need to find this D A to A dash. So this D A to A dash distance is calculated by taking this right angle triangle. Now here this total distance is 6 meters and here this is 4 meters. So this value will be under square root 6 square plus 4 square. So this value is 7.21 meters. Okay, so now you got the distance from A to B, A to B dash, A to A dash here. So now the distance from A to A dash, it will be same as the distance from C to C dash also, right? Now the distance from A to B you calculated, and the distance from A to B will be same as the distance from C dash to B dash, as well as B to C, as well as B dash to C dash. All the distances will be the same. Okay, and you also calculated the D A to B dash, right? So A to B dash you calculated. Now this distance is same as B to A dash, and also B dash to C and B to C dash. All distances will be the same here. Okay, so I will write here. So that's distance DAB. So DAB. So DAB here is nothing but this distance, right? So DAB. So this distance will be same as D C dash B dash, and which will be same as D B C. So which will be same as D C dash, sorry, A dash B dash. Okay, all these distances are same as DAB. Okay, similarly, so if you observe the distance DAB dash, AB dash here is nothing but A to B dash, this distance. So this distance is same as B to A dash, B to A dash also the same distance. It is also same as B dash to C. So B dash to C also the same distance, and also B to C dash also the same distance, which will be equal to 5.62 meters, right? So now, so from distance A to A dash here, so this distance D A to A dash distance will be same as C to C dash distance. Okay, so that now you got the all the distances in the given three-phase double circuit transmission line system. Now you can calculate the value of DS and DM. Right. Now for calculating the value of DS, you need to first find out the DS1, DS2 and DS3. Right. So now the value of DS1 will be equal to, you have to consider the first conductor. So first conductor here is the conductor A. Right. So if you are confusing with the DS1, DS2, DS3, instead of that you can even take it as cube root of DSA, DSB, DSC. Right. So we are going to find out the self GMD of conductor A, self GMD of conductor B, self GMD of conductor C. Okay. Now if you consider phase A, right? So here you have the conductor A as two phases, right? So one set you will be having one conductor A, another set you will be having A dash. So you have to consider these two conductors A dash, right? Now you have to write the product of all possible distances and whole to the power of 1 by 2 conductors are there, so it will be 2 square. You will get 4, right? So how you can write? So DSA is equal to, you have to write all the possible products by taking A and A dash conductors, right? So only A and A dash conductors only you have to consider, and you should not consider any other conductors, right? So for now, if you write the self distances DAA, if you take the conductor A, so DA is one distance and DA to A dash is one distance. So then if you take A dash, D A dash is one self distance and D A dash to A is another distance, whole to the power of 1 by, so total number of conductors whole square. So here 2 conductors are there, 2 square you will get. So this will be 4th root of D A D A dash D A dash D A dash A, right? And here the value of self distance D A and D A dash, this value will be equal to R dash. Okay, R dash is the geometric mean radius, which will be equal to 0.7788 times R value, and that value we already calculated here in the previous slide, which is 0.584 centimeters. Okay, right. So now this problem, this equation is similar to this equation here. Okay, 4th root of DAA dash D A dash A D A dash, right? So now here DAA and D A dash C dash, these are the self distances, you consider them will be equal to r dash. That r dash value is 0.854. Here and here you are getting 0.854. Now here the d a to a dash distance, right? So a to a dash distance, this distance is equal to 7.21 meters. So here we are taking 7.21 meters here. So in place of d a dash a, okay, 7.21 meter. Similarly, d a to a dash also the same distance, right? Now this is in meters, right? 0.854 is in centimeters. So the centimeters we are converted into meters by multiplying with the 10 power minus 2, right? When we multiply 0.584 with the 10 power minus 2, that value will also be converted into meters, right? So that all the values will be in the same unit, right? So now if you calculate the value with a calculator, so then the value of ds1 you are getting it to be equal to 0.205 meters, and the value of ds1 will be same as the value of ds3. So why? Because here if you take the conductor A and if you take the conductor C, so the arrangement will be for same for these two conductors, right? So the value of ds1 and the value of ds2 or ds3, so both will be the same, which will be equal to 0.205 meters, right? If you are unable to know whether how to know this value, instead of directly taking, you can even calculate the value of ds3 by considering the C and C dash conductors and taking all the possible distances product whole to the power 1 by 4. Okay, so right, else by observing the diagram itself, you can say that A and C conductors both are having the same position. So both the values will be the same. So which will be equal to 0.205 meters. Right, now the value of ds2 here is nothing but the value of self GMD by considering the conductor B here. So you can even take it as dsb, right? So dsb here is self GMD by taking B phase conductors, right? Here in B phase you are having two conductors B and B dash. Now I have to take all the possible products, right? So all possible product will be, so if you take B, so dbb is one product, then dbb dash is another product. If you take B dash, so then db dash b dash is one product and db dash b is another product. Okay, and here also dbb and db dash b dash, these two values will be equal to r dash here, so which is nothing but 0.584 centimeters. And if you want to convert into meters, you have to multiply with 10 power minus 2. So the dbb will be 0.584 into 10 power minus 2 meters, and dbb dash, so bb dash distance here is 5.5 meters. So this will be 5.5 meters, and db dash b dash will be the same as r dash, which is 0.584 into 10 power minus 2, and db dash b is 5.5. So the value here you are getting it to be equal to 0.18 meters. Okay, so now you got the value of ds1, ds2 and ds3, or dsA, dsb, dsc also you can say. So those values you got. So the value of self GMD for the overall three-phase transmission line system will be calculated. So by using this expression, so simply substituting all the values, right? ds is equal to cube root of ds1 is 0.205 and dsb or ds2 is 0.18, right? And ds3 is same as ds1, which is 0.205. So the value of ds finally you are getting here to be 0.195 meters, right? So this is how you can calculate the self GMD in case of a double circuit transmission line system. Okay, so now how you can calculate the mutual GMD. So now for calculating the mutual GMD, the formula here is the dm is equal to cube root of dab, dbc and dca. So now here dab is the mutual GMD by considering the phases A and B, right? So you have to consider the phases A and B, and in phase A you have A dash conductor, and if you, in phase B you have B dash conductors, right? So now you have to take the mutual GMD between these phases A and B, so that is called the DAB, right? So DAB is the mutual GMD of two conductors or two phases A and B, so in which you are having the conductors A dash and B dash, right? So now the value of this DAB is equal to, you have to write all the possible mutual distances here. So mutual distances here is in the sense, if you take A here, So the mutual distance from A to the phase B will be DAB and DAB dash, right? These two. So this is one product, DAB and DAB dash, one product. Now if you take the A dash conductor, then A dash B and A dash B dash is another product. So D A dash B, A dash B dash, D A dash B. Okay, whole to the power of 1 by Mn you have to consider. Here in phase A 2 conductors and here also 2 conductors, 2 into 2, 4. So 1 by 4 you will get. Okay, so the value of DAB here will be equal to 4th root of DAB, DAB dash, D A dash B dash and D A dash B. Okay, so like this you can calculate the mutual GMD by considering 2 conductors at a time. Right? If you consider 2 conductors or 2 phases A and B, so by using this formula you can calculate the value of mutual GMD between phases A and B. Right? So now the value of DAB is the distance from A to B. So A to B distance we already calculated. Right? So the value of distance A to B we are calculated will be equal to 3.1. So from the previous slide here. So distance from A to B is 3.1 meters. So that 3.1 meters you have to substitute here. So then what is DAB dash? So AB dash here is nothing but A to B dash distance. This A to B dash distance also we calculated. So that value is 5.62. So then DA dash B. So A dash B here is this distance and this distance is same as DAB dash distance. So the same value 5.62 you have to consider. And DA dash to B dash. A dash to B dash in the sense this distance. And this distance is same as this distance. So that value is 3.1 again. Okay. So now if you calculate this value, so the value of DAB, you are getting it to be equal to 4.17 meters. Right. So then the value of DCA also you can calculate by considering the phases C and A. And in C you have C dash conductors and A you have A dash conductors. Right. Now you have to write the all possible products here. So the products will be C to A, C to A dash. So the distance C to A, C to A dash. So then if you consider C dash to A and C dash to A dash, these are the mutual distances. So D C dash to A, C dash A dash. Okay, whole to the power of 1 by Mn you have to consider. Here also 2 and here also 2 conductors. So 2 into 2, 4. So that will be the 4th root you will get. Right. So 4th root of DCA, D C A dash, D C dash A, D C dash A dash you will get. And the value of distance from C to A here. C to A here is nothing but this distance. So this distance is total 6 meters. And C to A dash here is this distance. So which is 4 meters. And C dash to A here is C dash to A. So this distance which is again 4. And C dash to A dash. So this distance again 6. Okay, so if you calculate this value by taking 4th root, so then you will get 4.9 meters as a DCA value. Okay, so now, so this DAB will be same as the DBC. Why? Because DAB and DBC position, if you observe, those are symmetrical. Okay, so the value of DBC also will be same as DAB. I'm not going to calculate the value of DBC. So I'm directly taking the DBC will be equal to DAB. Right. So then finally the value of DM will be equal to cube root of DAB, DBC, DCA. Simply substitute the value of all these 3 parameters. So that DM is equal to cube root of the value of DAB here is 4.17 meters and DBC also will be the same 4.17 meter and DCA is 4.9 meters. Right. So taking the cube root you will get 4.4 meters. Right. So this is the value of DM. Okay. So the value of DM you got 4.4 meters and the value of DS here 0.195 meters. Right. So then the inductance per phase per meter length will be calculated using the expression 2 into 10 power minus 7 ln dm by ds here. Right. So the value of dm here is 4.4. So this will be equal to 2 into 10 power minus 7 ln. So 4.4 meters is dm value and ds value is 0.195. Right. So ds value 0.195 you have to write. Right. So now if you calculate this value with the calculator, so you will get the inductance per phase per meter length will be equal to 6.23 into 10 power minus 7 henries. Okay, so this is for 1 meter length, right? So inductance per phase for meter length, right? So this even can be written as 0.623 into 10 power minus 3 millihenries. Or if you want to convert this inductance per phase to kilometer, right? You have to multiply this total value with 1000, right? Then the inductance per phase per kilometer you will get by multiply with 1000. So that value finally you are getting here to be 0.623 millihenries. So this is how you can determine the inductance of a double circuit 3-phase transmission line system. Okay. So if the conductor configuration is given like this. Okay. So sometimes the conductor configuration even may be given like this in a straight line. All the 3 sets will be given. So the same procedure you have to follow for this type of problems also. Okay. Right. So we will see the another configuration of double circuit transmission line system in which all the conductors are placed on a horizontal plane. Okay. So now read this numerical problem number 6. Right. So determine the inductance per kilometer per phase of a double circuit 3-phase transmission line, which is shown here in the figure. And the radius of each conductor is given as 1.5 centimeter. Radius of each conductor R is given as 1.5 centimeters. Okay. So then you have to calculate the inductance per kilometer length for each phase in a double circuit transmission line system. Right. In this configuration, if you observe here, so this configuration is a horizontal configuration. Okay. So ABC is one set here and A dash B dash C dash is another set. Okay. So this is one set and this is another set of 3 phases. So one set of 3 phases, another set of 3 phases. Totally you have 2 sets of 3 phases. So this transmission line system is called a double circuit 3-phase transmission line system. So for calculating the inductance of this double circuit transmission line system, also we have to employ the same procedure what we have done for the previous problem, right? So the inductance equation L is equal to 2 into 10 power minus 7 into ln dm by ds. So this is the value of inductance in henries per meter, okay, per phase. Okay. So now here the value of dm will be equal to cubed root of dab, so dbc, dca. Okay, and the value of ds will be equal to cubed root of dsa, dsb, dsc. Again here the dab is nothing but this is the mutual GMD by considering only phases A and B, and dbc is the mutual GMD by considering only the phases B and C. So dca is the mutual GMD again by considering the phases C and A, and dsc here is nothing but self GMD of conductor A alone, right? And dsb is the self GMD of conductor B alone. So dsc is the self GMD of conductor C alone. Okay, so total self GMD if you want to calculate cube root of all these 3 values you have to take. Okay, so here, so dm is equal to dab, dbc, dca whole to the power of 1 by 3. Okay, now the value of dab, how you can calculate? So while calculating the value of dab, you have to consider the phases A and B. So this phase is having A dash, this phase is having B dash. So all possible mutual distance products you have to consider. So which are dab, dab dash. So dab, dab dash. So here we are represented with a small letter. The distance is represented with small letter here. You can use any designation also, right? So d here distance from A to B. So then distance from A to B dash one product. Now if you consider this A dash to B, A dash to B dash, A dash to B, A dash to B dash, whole to the power of 1 by, so 2 into 2 you will get. So here 2 conductors are there, here 2 conductors, 2 into 2 will be 4. So whole to the power of 1 by 4 you will get. Okay. So now, so what is the distance here? DAB. So DAB distance here is D. So then DAB dash. So DA to B dash from here to here. The distance is D plus D plus D plus D plus. Total 4D you are having. So then DA dash to B if you see. So A dash to B. So A dash to B here from here to here. So this distance also 4D. So then A dash to B dash if you see. So this distance is D. Okay, and so the value of D here is given as 1.75 meters. So from this equation, you will get 4 square into d power 4 whole to the power of 1 by 4 you will get. So this will be same as so 2 into d whole to the power of 2 into d you will get, so finally, right? So 2 into 1.75, so will be the 3.5 meters. Okay, so then so dbc also you can calculate in the same way. So right, for calculating dbc you have to consider b and c. So here b is having b and b dash conductors, and c is having c and c dash conductors. Now all possible mutual distances will be d bc dc dash bc dash dbc dbc dash one product. This is db dash to c, b dash to c dash is another product. Whole to the power of again 2 into 2 4 you will get. So 1 by 4 you will get. Again the distance dbc. So dbc here is d, and b to c dash will be 2d, and b dash to b dash to c, this distance will be again 2d, and b dash to c dash is d here again. Okay, so now if you calculate this value, you are getting 2 square into d power 4 whole to the power of 1 by 4. So this value is equal to 2 power 1 by 2 into d you will get. Okay, simply root 2 into d can say. So root 2 into 1.75 if you calculate, so then you will get the value to be equal to 2.47 meters. Okay, in similar way you can calculate the value of dca by considering phases c and a. So in which c is having c dash conductors and a is having a dash conductors. So all possible distances dca dash c dash a dash distances, all products you have to consider whole to the power of 1 by 2 into 2 4. So this you will get. Okay, again ca c a dash c dash a c dash a dash, all the distance you can obtain from so this diagram. And if you take the product and if you substitute the value of d will be equal to 1.75 meters, finally you are getting dca will be equal to 4.28 meters. Okay, so now you got all the values dab dbc dca here. Okay, so if you observe all these three values are different. So in the previous problem, so dab is same as dca. Why? Because symmetrically those two values will be the same, right? If you observe the conductor configuration in the previous problem, so those are symmetrically placed. Because of that reason only they are same. So here those are not symmetrically placed, so here all values will be different here. Okay, so the value of dm here is 3.5 2.47 4.28 whole to the power of 1 by 2, so 1 by 3. So the value you are getting here is 3.33 meters. So the value of dm mutual GMD is 3.33 meters. So then calculate the value of ds. So ds here is the equation is dsca dsb dsc whole to the power of 1 by 3. So now again dsa is the self GMD, self GMD by considering the phase A, and dsb is the self GMD by considering the phase C, and dac is the self GMD by considering phase C, right? So now calculate the first dsa. So now this dsa you have to consider, you have to calculate by considering only phase A, right? This phase A is having two subconductors a dash here. So you have to write all possible products by considering only these two conductors, right? So dsa will be equal to, the possible products are daa d dash d dash d dash whole to the power of 1 by total number of conductors square, 2 square you will get. Okay, so this is the equation. Okay, and the value of daa and d dash this value will be equal to r dash, which is 0.7788 times the r. Okay, so this we are going to write here, right? So see here, this is daa is r dash, a to a dash distance. So a to a dash distance, if you see, this is the distance, this here distance to distance, total 5d you are having. So this is 5d, a dash to a dash same again 5d, a dash to a dash r dash, here you will get whole to the power of 1 by 4. This can be written as r dash 5d whole to the power of 1 by 2. Okay, so r dash 5d whole to the power of 1 by 2. R dash here is the 0.7788 times r. We are writing here 0.7788 times r value here is, here in the problem it is given as 1.5 centimeters, right? 1.5 centimeters. If you want to convert into meters, you have to multiply with 10 power minus 2. So then this value will be 0.01 0.15 meters you will get. So that we are going to substitute here. Okay, so R dash value is 0.015 meters multiplied by 0.7788, and here 5. So D here is 1.75 whole to the power of 1 by 2. If you calculate the total value, you are getting DSA will be equal to 0.32 meters. Okay, so then DSB also you can calculate in the similar way. So by considering the phase B only. Okay, here in phase B, B dash conductors are there. So if you write all the possible product, B dash, sorry, B dash, D B dash B dash, D B dash B whole to the power of 1 by 4 you will get. Okay, this D B dash B dash. So these two will be R dash, so R dash square, and B to B dash, if you see the distance is 3D. So 3D whole square you will get whole to the power of 1 by 4. So which is R dash 3D whole to the power of 1 by 2 you will get. That's R dash 3D whole to the power of 1 by 2. R dash is 0.7788 times the 0.015, and 3, and D is 1.75. Okay, so whole to the power of 1 by 2 if you consider. See here, here one it is missing 0.015 have to consider. Whole to, so that our total value are getting it to be equal to 0.2476 meters. Okay, and DSC also you can calculate in the similar way by considering phase C, in which C dash conductors will be there. You write all the possible products and whole to the power of 1 by 4. Then you will get R dash D into whole to the power of 1 by 2. And if you substitute the R dash value will be 0.7788 times R here is 0.015 and D is 1.75. Then you will get final value to be 0.143 meters. Okay, so now you got the values of DSA, DSB, DSC, whose values are 0.32, 0.2476 and 0.143 respectively. So now all these three values we are going to substitute in this equation for getting the self GMD DS. So DS is equal to 0.32, 0.2476, 0.143 whole to the power of 1 by 3. So if you calculate this value, you are getting DS will be equal to 0.2246 meters. Okay, so DS value got 0.2246 meters. On the previous slide, DM we got 3.33 meters. Now you can calculate the value of inductance per phase per meter length. So this will be equal to 2 into 10 power minus 7 ln DM by DS. And the value of DM here is 3.33 meters and the value of DS is 0.2246. Right. So if you substitute those two values here in this equation and calculate the total value, the value of inductance per phase per meter you will get. So then again if you multiply that value with 1000, you will get the value in terms of kilometer, right? So finally the value we are giving here, the inductance per phase per kilometer value, if you calculate the value, you will get it to be equal to 0.539 millihenries per kilometer. So this is how you can calculate the inductance of a double circuit 3-phase transmission line system. Okay, so in a double circuit 3-phase transmission line system also you may be having 3 types of configurations. In one type of configuration you will get the conductors like this. So this is one set and this is another set. So this is one type of configuration. In another type of configuration you will get the conductors in a straight line, one set in straight line, another set will be in this right line. So representation will be A, B, C. It will be opposite. A dash, B dash, C dash. Here also A, B, C, A dash, B dash, C dash. And in the third configuration, you will be having all the conductors in a horizontal plane. So A, B, C. You have another also horizontal in the reverse direction. A dash, B dash, C dash. Okay. So this is one set and this is one set. Together it will form a double circuit transmission system. Right now we determine the inductance of double circuit transmission line by considering the first configuration and third configuration. And for the second configuration also the procedure will be same as for the first configuration, and you can even consider any one example and you can do on your own also. Okay, right. With this I'm concluding the session. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.